So our basic idea of simple volumes is just we're adding slices of circles together, and the integral allows us to make these slices so infinitely small that it becomes a smooth curve out. So dx is just a little bit of width times my r squared, pi r squared, which is our circles. So it gives us little tiny volumes. So it's pretty much looking like little shells being added to each other, giving us an object. Okay, now we're going to spin this around a different way today. So we're going to spin around the y-axis. And our first example is going to be already kind of spun around. X is equal to negative y squared plus 4. And we're going to bound it by x equals to 0. Now to plug this in, let's go ahead and plug in y values. Now this graph is spun in a different way. We're not plugging x's now, we're plugging in y's. So if I plug in y is 0, x would be 4. If I plug in y is positive 1, x would be positive 3. If I plug in y is positive 2, 2 squared is 4, negative 4 plus 4 would be 0. The parabola would actually curve this way. If you guys remember from algebra 2, if it's y squared, it's a parabola going to the right. And since we have a negative y squared, that's why it's going to the left. If I plug in negative 1 squared becomes a positive 1. And then negative 1 plus 4 is back to 3. And then we're going to get a mirror image on the left side. And for us specifically, we are only stopping at x equals to 0. So we're looking at this shape here. Now, on AP Calculus test that is no longer a thing, did you guys, are any of you guys going to take the makeup exam? You guys all did submissions? Okay. Good. Okay, so we're going to spin this around the y-axis. I'm going to pick a different color. Spin around this way. You end up with this kind of shape going this way, curving out this way. Now, if you take one slice of this, let's take this one slice here. This looks more like a pancake, a circle. When you spin something around, it makes a circle. So we do exactly what we did before. We say we're just adding up circles. And the circle here is pi r squared. What's the r value? The r value is the distance from the axis of rotation to the function. And that is an x value. See, isn't that an x value? That's an x value. And they gave us the equation. So just like before, we go integral pi r squared. And instead of doing dx, because x's are little slices, like little widths, we want slices of height. So we're looking at a little bit of dy. So the volume measurement for us is actually going to be very similar to our rotating around the x-axis. So we end up with pi r squared dy, where r value here is going to be pi integral of the r is our radius, which is our x value, like we mentioned. See our x value, how far we came out. X value here. We're going to write this as parentheses negative y squared plus 4 dy. Oh, I forgot the square, sorry. So these equations look literally mirror images of what we had before, right here. The things that we have to be careful of is what is our r value. In our first version, when we're rotating around the x-axis, that r value is this height here, which is just a y value, or f of x. But in our rotation around the y-axis, our r value is this guy here, which is an x value. That's an x value. So we have to make sure you choose the right x or y value. besides that, it's just pi r squared. Now, this is if they give you the variable that you wanted. Let me say this again. If I'm spinning something around, let's say I'm going this way. If I'm spinning it around the y-axis, this is my r. If I'm spinning this around the x-axis, this is my r. So it could be the same equation, but it changes based on which axis I'm spinning. And that's the part that confuses kids. So let's use this example from a very simple one. Let's say this is y is equal to the square root of x. Something very simple. And we'll go from 0 to 1. Oh, I need to put the boundaries over here. For this graph on my left, we started at positive 2 to negative 2. So the y values crawl from negative 2 all the way up to 2. We do slices like this, from negative 2 all the way up to 2. Our example back here, we went from 0 all the way to 2. 0 all the way to 2. Okay. So our version here, we're going to go from 0 to 1. And if I plug in the square root of 1 is 1, so just FYI, this is also 1 in the y. So I'm going to do this problem very quickly in 2 rotations. So first rotation along the x-axis. Along the x-axis, the graph spinning this way gives us, look, a nice circle here. From 0 to 1, integral from 0 to 1, and we created circles, that's pi r squared, where r is the equation, y, which is just square root of x, with little slices of dx. Little slices of dx. But if I want to spin this in the y direction, along the y-axis, this graph here actually spins out and looks like a little tornado. Oops, I can graph that way. Looks like a tornado. So this is our shape here. So how do we count this? Well, starting from 0 going up to 1, it's the integral from 0 to 1, and we said that shape is a circle, so it's pi r squared, but the r here is an x value. But our problem is y is equal to square root of x. This is a y value. We need an x value. So what you do? Solve for y. Sorry, solve for x. So if you solve for x, the way I get rid of a square root is a square. Y squared is equal to x. So you have to rewrite the equation for these problems. You rewrite the equation to get the variable that I need. I need here an x. That's my radius. So given the equation of the graph, I need to rewrite this to become an x. And if I rewrite it, x is now y squared. And that's my r. This is a little bit of dy. And we're going to square it. So our basic idea is that if I'm going to rotate around a particular axis, I have to make sure I have the correct variable. And the main variable I'm looking for is the radius, and the radius can change. Is it going to be on my left here, a y value going up and down, or is it going to be an x value going left to right? That's really the biggest takeaway here. So let me go ahead and give you guys another example here. Let's see, I have my file here. And you can see on these problems, that I'm spinning along the x-axis going this way. So if I'm spinning going that way or this way, what's my r? My r is an x value. They gave me the equation for x. Spinning this way, my r is an x value. They set me up perfectly. So these equations are ridiculously easy. It's just a circle pi r squared, where r is negative y squared plus 4, because that's the distance right here. One on my right, oh, sorry, dy. The integral pi r squared, where my r value is really the x value here, which is already given. So square root of y squared dy. Now, we're getting to a place that is a little awkward now. This is written sometimes in two different versions, because if I wrote this as one version, it fails the vertical line test. That's the only reason why they wrote it this way. A square root graph looks like half a parabola. And if you give me the negative part right here, see that negative? It's just the mirror image of it on the bottom. So that's why there's actually one graph on top and actually a separate graph on bottom with that negative sign. So for us to rewrite this equation is, let's first ask ourselves, which way am I spinning this? I'm spinning this along the y-axis, so we're going this way. So I need a x or y for the radius. I need a x value. We were given not an x value, we are given a y value. So this is where we have to rewrite the equation, like we did in our example previously. If I say y is equal to the square root of 4 minus x, how could I solve for x here? You would get rid of the square root, then get rid of the 4, and then in this case, to get rid of the negative sign. Get rid of the square root first, dig out the 4, then dig out the negative. So back to algebra 1. So y squared equals to 4 minus x minus 4 minus 4. Y squared minus 4 is equal to negative x. X equals to negative y squared plus 4. And that is our sideways parabola, facing left because it's negative. So now that we have the equation for x, the equation is pi r squared, where my r value is going to be an x value, and the x value is negative y squared plus 4. And this is a dy. Look at the graph. We go from negative 2 to 2, climbing up, negative 2 to 2. On the right side, our next example here, we are rotating again along the y-axis. So we're making spinny circles this way. So we need to find what the radius of these circles are. And is that going to be an x value or a y value to find that radius of my circle? This is going to be an x value. Did they give me an x value here? Nope, they give me a regular parabola. All this other stuff here are just boundaries. Y is 4. X is 0. X is 2. These are just my boundaries. So really the graph is y is equal to x squared. Y is equal to, sorry, whoops. So the volume is equal to the pi r squared integral of circles. We're going to take this from 0 all the way up to 4, crawling up 0 to 4. And pi r squared, my circles are for my r value. We said that has to be an x value, doesn't it? So how can I make y is equal to x squared an x value? Solve for x. Take the square root of both sides. Plus and minus. Now we want to be aware that, let me see. Whenever I take a square root, I need to include a plus and minus myself. Yep. So which graph would I use here? Thinking the positive one. If x is, that's right, square root equals to x minus square root of y equals to x. If x is positive 1, sorry, if y is positive 1, x is positive 1. If y is positive 1, x is negative 1. So am I using this version here or this version here? According to my graph, I only want the right side. I'm only looking at this one. So my r value is just going to be square root of y. Okay, let me go explain that again. Whenever you take a square root, you always have a plus and minus version. And if you look here, we do have two versions here. We have a positive version on the right and a negative version on the left. So that's my positive version on my right, and this is my negative version on my left. And I plugged in the point just to verify in case I got confused. The graph that we're using is only the positive version on the right. So I can only use the right version. Does the problem get much difficult than this? Yes and no. If you look at this next one, it really is skills from algebra 1 and 2 to solve for that variable. And x would be y squared. And this is a parabola y squared. But we're not using both sides. We're only using the top side. But lucky for us, we can stop that because it goes from 0 to 1. Those are the boundaries of my integral. My r value is, we said y squared, dy squared, and then let's stick a pi in front, pi r squared. And remember to do the square here? Nope, I forgot to do a squared here. Pi r squared, pi r squared. Whoops, keep forgetting to do that squared. Pi r squared. Okay. That's pretty much the examples for rotating around the y-axis.